我们下午时间差不多了，我们可以现在开始。然后非常感谢，王Feng-Bin教授给我们下午精心的准备了break time 的 tea time。现在我可以过一把 English 的那个 British 的 break。对，那边有茶，然后也有小点心，欢迎大家随时去那边去补充能量，因为下午这个今天第一天的确是有点长，而且明天事实上就是 Christmas。然后你们好像也放假，不是 Christmas for some other reason，right？对，我不知道是明天是一个什么 holiday。对，先跟大家说一声 Merry Christmas。对，那上午的时候我们讲完了 DTMC，如果就是 for some reason 你要是 miss 的话，也许可以跟周围的同学感兴趣的话可以借笔记看看。好，然后有问题再跟我讲。So in the afternoon section, we're going to talk about another stochastic process, which is known as continuous time Markov chain. So first, let's take a quick review. How will you find DTMC? It looks like the difference is time. One is the time index is on a discrete space. The other one is on a continuous space. The DTMC is what? First of all, for any n, this means non-negative integer. This basically means so fixed n, fixed step of time. 这是一个 discrete random variable. That's why it's a chain. 然后第二个，它要满足什么？因为它叫 Markov， 对吧？有 discrete time， 有 chain， 就是 chain 是 discrete time， discrete random variable， 这说明它是 discrete in time， discrete in state space。那现在就剩一个 Markovic。What's Markovic？ Markovic 是 probability future。Markovic 是什么 ？Future only depends on present, is independent of history, the past。这个是什么？这是当前，对吧 ？Current time span。这个是 next step。这个是什么？就是 history, anything before。这些都是 history， 这是 up to now。它如果是 Markovian， 它是怎么定义的？就这个。那我们现在来看一下，然后 what do I mean by a continuous time? A stochastic process. First, we see the difference. Time is defined on 0 to infinity. So because many of the situation we say t is the time. So that's why I start at 0. Initial time is all of a sudden, let's say it's 0. It's called a continuous time. Okay. CTMC. If, first of all, for any t, This has to be a discrete state space. Discrete random variable. Then the other one, we're not, the better way I think is filtration, but that's too fancy. It's equivalent to the following. For any T0, the probability given anything in the past is Markovian's only depend on French. So what's T1, T2, T3, Tn? I haven't said that. That's a time realization of the waiting time. So I'll draw that in a second. Give me a second. Let me draw that first. We want to do this because we want to compare this to DTMC. So let's define WI is the ice waiting time. Ice jumping time. So start from very beginning. Here is the starting point. Now I jump. So this is W1, W2. This is W3, etc. Then the time in between. This is T1, this is T2, this is T3, this is first round, T4. So this is defined to be what? Wi plus 1. And then Wi. This one is Ti. Is the integer. So this is what? Waiting time, I'll call it holding time, called surge on time. It's all the same thing. Waiting time, surge on time, and inter-arrival time, inter-event time is all those. Is the time between events. And here is the jumping time. So we talk about for each realization of this time point, jumping time point, we have the following. Does this make sense? Then here is a quick comment. So Tn is inter-arrival time or waiting time. Inter-arrival or waiting time.它是一个什么？它是一个 random variable. That's the fundamental difference between DTMC and CTMC. In DTMC, what happened? You have, it should be, everything should be equal. So this is 0 step, and first step, 2 steps, 3 step, and 4 step. And basically the thing's going to happen on a regular time series basis. So this time, whatever you call, is fixed. It's a constant. But for CTMC, the inter-arrival time is a random variable. And this is what the second property we just saw in a minute. This is called Markov property. So the process basically saying it's a memoryless. It's a memoryless. And we know, indeed, this can be shown. Indeed, the only continuous random variable has or satisfy memoryless property is the exponential distribution. I hope you guys see the fundamental difference between DTMC and CTMC. In DTMC, the waiting time, maybe we can put it here. Still, TI is the ith interarrival or waiting time. For DTMC, everything happen or occur, take place on a regular time basis. Time in between, they're all equal. So the waiting time TI is constant. But for CTMC, this is some exponential distribution with a rate, whatever. So we'll figure out later. And then if it's a random variable, and so the waiting time can happen anywhere between 0, of course, technically speaking, infinity, any positive time can really happen as soon as you wish. And as far as it goes, of course, the probability is going to be different. And so for this one, and CTMC usually is good for what? The application. When you study stochastic process, we should talk about what? With discrete change. But when it happens, that occurs or that takes place at irregular time points. There are too many examples. See, chemical reaction, it can happen anytime. An epidemic, and say the simplest will be birth and death, and like Kaohsiung process. Simple birth and death. Each step, either you're giving birth to one more, or and you lose one for some reason. Birth and death process. And say epidemiology, biology, chemistry, physics, finance has way too many applications. And the key point is the waiting time. It's going to be what? Exponentially will be follow a exponential distribution. Do you guys remember exponential distribution? Say T is exponentially distributed with parameter lambda. By definition, we know any random variable can be uniquely characterized by its probability density function, cumulative distribution function, moment generated function, characteristic function. Let's take one, say PDF. Then the PDF, say CDF is okay. The CDF T is a probability less or equal to T. It's 1 minus e to the negative lambda T for T is greater or equal to 0. So once you see the CDF, and you will know this follows some exponential distribution. So what's the opposite? Or what's the complement? What's the probability waiting time is longer than T? Will be 1 minus the whole thing about, which is when you see either cases, and you know you are working with the exponential distribution. Question? When you see either of those, they're equivalent. All right. Is the question clear? Oh, sorry, is the definition clear? once we understand this should be pretty easy to see this. Again, this is T0, T1, Tn is not arbitrary point, it's your, say Tn is your nth jumping point. T0 is where you start. Anyway, all right. So without loss of generality, we are assuming the state space. The state space. Of the TPNC is equal to what? Is it equal to non-negative integers? Then for each t greater or equal to 0, we know this is a random variable. So the random variable, the xt, has the corresponding probability distribution. Probability distribution. Fixed t is a random variable. What this means? PIT is the little p we talked about in the morning, similar to DTMC. So little p is equal to the probability at time t you are in state I. That's all. And now, of course, the state space can be anything. You can define anything you like for the state space. We're just saying could be on the integer, could be on the whole lattice, could be anywhere. We just say without loss of generality, here is how the state space works. All right. So then little p of t, the vector in 0t and t is just like a HIS model, but that's for DTMC we saw in the morning. And that t is not arbitrary t, that's integer, like 0, 1, 2, 3. It's discrete in state space, sorry, discrete in time. But right now, this t is continuously changed over time. All right. So this is the vector of the probability distribution. Then you were wondering, since for DTMC, we spend so much time something called transition probability or transition matrix, right? So what happened to the continuous case? Transition probability. Of the DTMC, sorry, CTMC. Defined by forms. So this is saying at this time s, m as state I. Here's time s, here's time t. Of course, t is, and it's higher. So this is the transition probability from time s to time t. Then your transition is from state I to state j. So very similar to the transition matrix we saw for DTMC, right? And the only difference here is only taking integer level, right? Yeah. And then, of course, if the transition probability is independent of specific S starting time point and ending point specific T, only depends on time length. Just like before, here's N, here's N plus 1. If it's independent N, where I start, because we keep tracking of starting point and the ending point, that case, and this process or CTMC is known to be, or is going to be said to be homogeneous or stationary. So P only, what's the right word? Only depends on the time length. E minus S and not depend on and does not depend on the time, specific time points S and the T. In this case, the corresponding CTMC is said to be homogeneous. Very similar idea, right? As we saw for DTMC. DTMC only difference S is integer, T is integer. So when we see the step transition, one-step transition, if it's independent, which N we start with, only depends on time length, that time is one step, it's called one-step transition. So it's homogeneous. 林老师 or something also known as stationary. Otherwise, the DTMC inhomogeneous or non-stationary. So as I said, we probably for today's class, we're not going to talk about anything like that. Think about when you study disease, so many other things. And seasonality could play a super important role in the disease or epidemic you care about. So in other words, and you will have time-dependent periodic change, some functional parameter, say for instance, which depends on time. In that case, there's no way and the corresponding CTMC will be homogeneous, must be in or non-homogeneous or non-stationary. You guys with me? What this is saying, this is the analog of homogeneous DTMC. This is for CTMC. Before here is say N plus 1, right? This is the current time and the future. Here is the transition state. This is the independent S, independent specific choice, only depends on the difference. Like before, it's N to N plus 1, that's one step, the one-step transition, the homogeneous. So far, so good? Are we together? Can可以吗？好。这里有一个 quick remark. So do we remember when we talk about DTMC? What's a column sum? No matter you have finite many state space, you have only finite many options or infinitely countable options. The column sum must be 1. For continuous time, that's not the case. Here is just a warning, okay? This is something called explosive, just for your own knowledge. Explosive process. What's this mean? Roughly saying, infinite amount of time, you can have infinite many jumps. Yeah. So a CTMC is called the explosive. I don't know how many of you guys probably have experience with PDE. PDE, there's some problem called blow up, similar. To be called explosive if it has infinite many jumps. Meaning the process blow up in finite time. Infinite many jumps in a finite amount of time. Because not like before, you have 0, 1, 2, all on a regular basis. This can happen as soon as you wish. Of course, can be as long as you wish. It just has a different probability. So if we have a homogeneous CDMs, now the transition probability only depends on what? Only depends on the time length. So for short, we define this to be P probability minus cost. Stationary case. Anyway, for this one, now we say we know for explosive case, there's no guarantee. Here's a warning. There you are. Indeed, we usually may have, or we often may have J is all the possibility, isn't one. Now you're wondering, now the column sum is not 1. What happened? There's still some room left. Because what? You transition to the infinity, there's a positive probability for that. The missing part is counting. So because the infinite many jump, you jump to what? Infinity, right? So there is a positive probability. That's not in any specific state. It's 1. Sorry, it's positive. So that's why you have the missing part. The column sum may not be 1. Okay. So now, for today's discussion, from now on, we are assuming all the CTMC we consider, they are homogeneous and non-explosive. Say for instance, for this time, you see this summation less than 1 is saying by time t, the process already blow up. That's all this is saying, not corresponding to any specific finite state. All right, so in what follows, what's the right word? We assume that the CTFC we talk about homogeneous, stationary, and non-explosive. All right. And then one thing, here's a quick note. You know, for homogeneous PTMC, you can use what to capture the whole thing? And I think towards the end, and someone actually talk about this. A homogeneous DTFC can be uniquely characterized by its transition probability matrix, right? Can be uniquely characterized by its one-step transition matrix. a single matrix. This is a single matrix. IGLT, doesn't matter. I hope you're not confusing. This means from J to I, not from I to J. I write the other way. All right. But for a homogeneous CTMs, you cannot characterize the whole process by a single transition matrix. You will need, what we need, family of what? Of transition matrix, or transition probability. Which is what? PGIT of PT. How is it defined? So we need a snapshot of everything. So what I'm trying to emphasize for DTMs, if it's a homogeneous, okay, for both homogeneous, this structure will be way more simplified. You only need one piece of information. It's called the one-step transition matrix P. However, if you're doing continuous time Markov chain, this T is how much time is spent, right? It left. This T is how much time it left. All T, you have to collect all this information. It's like snapshot, but you have to take a movie right now. This is just one photo. This is a snapshot of the entire movie. So you guys see the difference, right? Even though they're both homogeneous. So now, then you were wondering how we're going to characterize this one. This is time dependent, right? Yeah. Does that make sense? You with me? Questions, we want to understand what's POT. And first thing, remember for DTMC, we have something called Chang-Kolmogorov differential, Chang-Kolmogorov equation. Okay, all right. Chapman. Again, this is the transition probability of our CTMC. Homogeneous, non-explosive. I'm not going to say that. So everything now is homogeneous, non-explosive. Then it's satisfied. What's that? So let's see. From I to J, it takes me T plus S time. So what I can do, I can go from I to K, then from K to J. Here, let's say take S time. Here, let's say take T time, and doing the summation over all the possible K. Have we seen this before for DTMC? It's called Chang-Kolmogorov equation. And super easy to understand. You can do this using one-step method. here is a transition from I to J. This is saying I go through some K right here. And here I use time S, the remaining I use time T. Now I go from I to J, use S plus T. For people familiar with co-cycle condition, you must have seen this for evolution operator. So in the matrix notation, what this means? This means, all right. Right? You must have seen this before. For evolutionary operator, this is one of the co-cycle condition. Anyway, this is Feng-Bin cosmology equation. It's telling us if I know this, I'm going to know what happened at that time point. Remember before we do this is one, this is one, this is p squared, right? For DTMC. If this is one, and you keep doing that, you get Pn, right? But now we have this. So one can easily prove this by one-step procedure. Now, to understand CTMC, we better have a really clear picture about something called Poisson process. Do we still remember what's a Poisson process? Roughly, do we have an example that something must be a Poisson process? Any example? No matter CTMC how complicated, if we understand this, we should be able to understand any general CTMC. First of all, if you have an example or like some example in your mind, think about like you guys' case. Everyone have phone. So then if T is the time, let's say XT is number of text message you receive by time T. As time moves, and this you get a collection of random variable. And each fixed time that can be approximated or formulated by something known as Poisson distribution, the collection of Poisson distribution. That is a Poisson process. And basically we did this when we reviewed our basic probability, is roughly speaking, is a counting process. All right, here is our first result, how to understand Poisson process. Assume we have a CTMC. Again, we assume all the state space. I already did that. I'll just emphasize. State space. All the possible state you could ever have. That has a following property. If this is a counting process, a Poisson process, let's do this. At time 0, you start to record the number of, say, text message you're receiving. Start at time 0, you haven't done anything yet. So number of the text message you receive is 0, right? Then let's look at for P bigger than 0 and sufficient small. Let's look at the infinitesimal. Transition of a word. Infinitesimal just means this one is really, really slow, conversion to zero. Instantaneous almost. Probability are given by this is saying start, because of homogeneous, I only need to track the time change. Delta T is the time change. Now, this is saying currently you have a text message and going any delta T time. And what's the probability you're going to have one more, you're going to receive one more text message? That's this. So this one, we know this means, right? This means, already let's spend more time. This means the probability given so this is the transition probability within delta T interval. It's independent of what T you start with. That's homogeneous. Anyway, this is definition. That's not part of assumption. This is equal to what? It's lambda delta T. This is the key. And the rest will be higher order compared to delta T. The dominant term will be this. And then also things could happen is within delta T, what's the other thing can happen? You're not receiving a new message, right? And what's the probability for that happen? No case. At any single time, you either receive one more new message or not receiving any message. Of course, this will be one minus that, right? Plus the higher order term. Then now you also will ask, what's the probability you go to any other, meaning you received here. This is saying you didn't receive any message. Sorry, I is you didn't receive any message. I plus one, you receive one more. This is anything else. Otherwise, that means you will receive more than one message. Could be two and above. What's this? This will be little o delta T. This is the infinitesimal, meaning when delta T is sufficient small, there exists at most one jump of Poisson process. Then the CTMC we consider is a Poisson process. And this one is super important. It's a Poisson process with rate. Just like your text message case, I said, any day you receive 20 text message, lambda will be 20. Okay. All right. So the key to prove the CTMC is the Poisson process, all we need to do is prove the waiting time is exponentially distributed. We did one simulation a couple weeks ago for Poisson process. The waiting time is exponentially distributed with parameter lambda. The key, so we define this one more time. Minimum amount of time. So we reach what? The answer jump. We don't need to say this. As inter-arrival waiting time. Inter-arrival. the key is to show, doesn't matter which one, T1, T2, T3, T4, they're all the same. They're IID. IID means identically independent distributed. Is exponentially distributed with parameter lambda. Once you did that and the process, because this is automatic guarantee and will be a counting process and which satisfy all the property processing process. The key is this. Okay, all right. Do you want to see the idea for this or you're fine with this? So this is the key we need to show. It's sufficient to show what? The first waiting time. And why all the others doesn't matter? Because every time when you come to jump to the first spot, and next times from first jump until the second inter-arrival time or waiting time, it's like you restart by Markov property. You restart, right? You do one jump again. Does that make sense? Because Markov property. So you restart, reboot. It's just like you do next jump as a first jump, right? Because you only can have, even something happen, you only have bursts happen. You don't have any other things. So it's sufficient to show this one is exponentially distributed. But we remember to show something is exponentially distributed, we can check PDF, CDF, and any of the characteristic of more generating function, right? All right, let's see this because this is super important. I hope you guys have a pretty good idea. Remember T1 is what? Infinite amount of first jump, right? All right, let's do this. Well, LT bigger than 0 sufficient small. And what's the probability the first waiting time is longer than T? What that means? That means you're not jumping yet. By time T, what happened? So we define this. Let's do this. By the infinitesimal time, if the waiting time is longer than whatever this time period, that means by this time, you're not jumping yet. If you're not jumping, you stay at 0, right? You haven't reached the first jump. You haven't reached the next spot yet. So you stay at 0. Because the waiting time of jumping time, a waiting time is higher or longer than this. Now what's this? What this means? What's this? This is saying what? Is probability delta T you remain at 0, given initially you're at 0. This is exactly what? This is exactly what? So right here. This is exactly by definition. This one, right? There's no jump yet. So what's the probability for infinite, when delta T is sufficiently small, infinitesimal time is this? Then we're almost done. Does this step make any sense? Then, because this infinite many amount of time, I take delta T equal to what? Equal to T over N, equally spaced. So then what happened? So you can see this equal to what? 1 minus lambda T over N. Now, from 0 to T, you do equal space partition. Here's delta T, here's delta T, here's delta T. and you have n copy. So then the probability you didn't see jump first spot. First interval is this, second interval also is this, because Markov property or independency. So the probability T1 is bigger than T. T is n times delta T. This is n times delta T. Is what? You have to guarantee no jump first delta T, second delta T until all the n delta T. And where the n coming from because independency. Then let's look at this. What's delta T? It's 1 minus T over n as n goes to infinity. Little n with T goes to n as n goes to infinity. What's this limit? Do we know what's this limit? That's it. Right? That's it. So this limit is where this show the waiting time is exponentially distributed. We probably only be able to, we don't have a lot of time. We probably only do the detailed derivation once. But what I really want to emphasize, no matter what CTMC we have, Poisson process is just one specific example. What's the waiting time? It's exponentially distributed. And for Poisson is special. This Poisson process, the waiting time is exponentially distributed with the same rate. In general, not going to be the same rate. All right. So now we see the trouble. We see the transition probability. We have to keep track of the whole family. So what we're going to do, we have to keep track of the whole family and doing everything. Like for Poisson process. So the transition matrix P delta P this looks like the following. And for this case, even though we have infinite many states, countably many, and the column sum is remain to be one, it's non-explosive, even if we have infinite many states. And also for any infinitesimal transition, we have at most one event could possibly happen. That's burst. You have got one more text message, that's burst. Now the key question, we have to solve our dilemma. How to solve, say, the transition probability. That's time dependent. Let me say, or Poisson probability. Because it's evolving in time, what are you expecting? Something is evolving in time. You're trying to get an equation or some sort of equation whose solution provide you the transition probability. That's our goal. Okay? All right, let's see this. Suppose the state is state I. This is the probability the process at time t is located at state I, PIT. Now let's do this one time. So this is a change called delta x. So now Let's see. This is the current time, and this is our arbitrary infinitesimal waiting time. Then what happened? For Poisson process is simple. There are only what? There are only two possible things can ever happen delta t time. So let's do that. What this means? This means xt plus delta t equal to I. Let's do one-step method. How we're going to get to there. How we could get to there. So now we keep track. This is t plus delta t. This is how much time is left. If we're able to get to state I, what can ever happen? What could possibly happen? We could, this is saying at time t plus delta t, you get a text message. You could have I minus 1 message, then you receive 1. You receive 1, what? See delta x t, you receive 1. And in the delta t time, that's one thing, times the probability of this happen. What else can happen? You could add this time step, you could have what? I message. And then delta x is equal to what? Equal to 0, no change. Then you can stay. And plus, sorry, times the probability for this happen, plus anything else, plus the change is k, given what xt is I minus k for all the possible k. K is not equal to 0, not equal to 1. Does this make sense? This is a one-step method, meaning how we could get to at time t plus delta t, the future time, give us I text message. So if we go one step backward, and from here, there are only two possible things can happen. If you receive one message, so at back to time t, you have I minus 1 message. Or you have same message, you didn't receive, you receive no new message during this time. And this is saying you receive more than 1 message, anything else.有没有问题？就是我们怎么到达 I 的嘛？因为它是 Poisson process， 只有什么？只有2件事可以 happen， 对不对？只有2件事可以 happen，either you burst or you stay。你或者 receive 一个新的 message， 或者是 no message。这就是这个和这个讨论的，这是 no message， 这是 receive one message。如果你 receive one message at the past time, you must have I minus 1 message to be able to reach I, right? 或者是 no change， 那你当然就是 T 了，对吧？就是 I go to I， 然后就是 anything else。如果你做这个的话，就得到了它对应的 differential equation。来看。所有的 homography differential equation 都是这么 derive 来的，叫 one step method。不管是 forward 还是 backward。好，我们来做一次哈。这个是什么？呀，我给擦了 ，sorry。这个是 the burst。Given current situation, you give burst 1, right? The Poisson process. That's corresponding to lambda delta t plus little o delta t. That's the first line. Sorry, I just erased that. And times the probability, this is what? Pi minus 1. Then no change. That's the second possibility. It's 1 minus lambda delta t. PIT. plus everything else. That's all the higher order. I shouldn't erase that. That's all coming from the theory. This is the definition. 就是在 time t you have I-1 message plus you give birth to one more message. What's the probability? Lambda delta t. And no new message is this. And you stay. Otherwise, it's higher order term. So what are you going to do next? You're going to subtract PIT and divide everything by delta t and write delta t equals to 0. So what do you get? You get dpi dt equal to lambda pi-1 p minus lambda pit. For on it is here. And initially, at time 0, we know there's no I message for any I is bigger than 0, that's 0. So we can solve the differential equation. So this one-step method, you can use that to derive all the homological equation or differential equation. Doesn't matter you are forward and backward. Similar method, one-step method. You're just moving one step, either forward or backward. And now I fix my future. So this is a backward method, one step backward. I see from which source I can stay at an I new message. Either I receive no message, that's one possibility, or I receive one message. So back to time t, I must have I-1 less message less. That's all this is saying. We discuss all the possibility, you can derive the corresponding what? Differential equation. So now if you solve this, and P0 is a little bit different because P equals to 0, you only have, you don't have this, I-1, -1. And also the initial is different, initial is 1. So for this one, we all know the solution for this, right? E to the negative lambda. So the general PIT, you see, it's e to the negative lambda t to power I factorial, I from 0, 1, 2, etc. So that's, you see, now we can figure out explicitly how the distribution look like over time by solving this indeed called homologous differential equation. Okay, all right. So the key is here. 我们要不要休息一下？下午是这个时间比较不好，我休息一下 ，fresh 一下，去外面喝一点茶水，然后吃一点点心，我们再回来。对，不用想太多，就是我希望你们能理解这个 method。No matter things how complicated it is, it's a one-step method. 所有的 homology equation 都是这样 derived 的。Anyway, let's take a 20分钟 break， 这样够吗？可以吗？我们来个20分钟 break， 我们3点25回来，好吗？好，休息一下。刚才讲的东西，我只需要就之前1个小时我们讲的东西，大家记住2件事就行。CTMC 有什么特别的？第一个 CTMC 和 DTMC 比较起来有什么特别的 ？What's something special about CTMC? Or what's the fundamental difference between CTMC and DTMC? 真厉害 ！Exactly, that's exactly right. Excellent. So the waiting time for DTMC is what? Constant. But for DTMC, it's a random variable, not arbitrary. It's what kind of random variable? 大家对 exponential distribution 有个概念，它一定是这样子的。 就是一定是这样子的，一定是这样的。刚开始的概率很高，然后概率会越来越低。它的 PDF 一定是这样子的，是 exponential decay 的。OK， 对，这是第一个。第二个就是刚才讲的这个是想用最简单的 CTMC， 我们现在用了一个最简单的 CTMC， 用 Poisson process 作为例子。它是一个 special example。如果我们能理解 Poisson process， 我们几乎可以做所有的 CTMC。idea 是什么呢？这个 PI of t 是 probability 在 time t 的时候 you're located as it is at。好，那现在从 t 开始，我 go delta t step step， 因为那个 delta t 不是一个 fixed time， 是 any time， 是有 probability distribution， 是 waiting time。我说给定 any delta t。如果你是 Poisson process， 只有2件事可能发生，你就想 text message 就好了。any delta t， 当这个 delta t 的 time span 足够小的话，你或者收到1条信息，或者没收到，它必须足够小。长了以后，你可能收到好几条信息，对吧？我说它足够小。那现在我们就看，如果在 time future time， 我过了 delta t 后 t plus delta t， 我要有 I 个 text message，how could that happen？那我现在就 go back to where I start time t， 对吧？如果 I didn't receive any text message， 那在 time t 的时候你也是 I， 对吧？也是 I 个 text message， 就是那个，对吧？然后它的 change 是什么？是 0， 没错。Take one step back。然后还有什么 possibility？ 我可以在这个 delta t infinitesimal time， 我可以 receive one new text message。If that happens at time t, you have to have what? I minus 1 message to become I message, right? 这样可以吗？你看，这是 given 这个 situation， 那你在这样，你 obtain 一个 new messages， 你就 become I minus 1 become I， 就是这个。这个是我在 time t 的时候，我就是 I， 我没有 receive any new message， 是 I go to I， 这是。For other case，other 无非就是 receive more than one message， 就是 higher order term。然后你把这个 plug in 以后，你就会得到一个什么？关于它的一个 differential equation， 它的解就是你想要的 distribution。这事实上是 Becker Kolmogorov equation 的一个特例。我想让你们知道的是说，这个叫 one step method。你可以 going fix the final thing going one step back。你可以 fix the initial time going one step forward。所有的可以说所有的 Kolmogorov equation doesn't matter your forward backward differential equation 都是这么 derive 来的，也不管你是哪种 case。All right， that's what we did。那因为这个 equation 非常 simple，step by step 我可以 solve 出来，我可以看到它的 distribution， 这 exactly 是 PDF Poisson distribution 的 PDF。That's all。而且这个时候的 waiting time 非常 special， 它的 waiting time， 它的 waiting time 是 IID 的，全是 follow exponential distribution with partial lambda。是因为什么呢？就是因为这个是什么？是 probability xt 等于零是什么？等于零是什么？这是 probability xt 等于 I 呀、这个是没有发生 by time t 的时候没有发生，是什么？一的 lambda t， 一的负 lambda t， 所以 exactly 就是它的 distribution。Anyway， 好， that's the first part。现在希望我们对一个最简单的，可以说是一个最简单的 CTMC 有一个比较好的了解，叫 Poisson process。那刚才我们说了，说去 capture 一个 CTMC， 我们要用什么？一个 family， 一个 movie， 一个 family of transition matrix， 对不对？是不是有点困难？ 所以我现在想找第二个 characterization， 叫 something called generator。就说这个刻画方式可以，但是我要知道所有的那个 P of T 随着 T involve 它是怎么做的。That's too much information， 对吧？现在是问你有没有第二个方式，或者是一个 better way， 我可以 capture this generation matrix 或 generation matrix。How many of you guys have seen SDE before? Okay, all right. So 这是 second approach， 我可以讲一下它的 idea 是什么。刚才我们说了 DTMC， 如果是好猫诊的，我现在都是好猫，我就不再重复了。是好猫 DTMC， 我只要它的 transition matrix， 我就可以 capture everything， 一个 matrix， 一个 single matrix。但是 CTMC 我需要知道什么？整个的 entire 的 trace 是一个 family of transition matrix， 一个是不够的，随着 time t 变，它一直都在变，对吧？它是会 evolve 的，是不是就感觉很 heavy？那现在我们想找另一个 alternative， 这个 something 叫 generator， 是什么呢？我们来看一下啊。首先我们 define initialize i time 0从 j 转到 i 应该是什么 delta ij， 只有它俩是一样的时候，你才会在那一点，否则你是没有时间没动的话，你是不会动。换句话说，这是什么意思？这是说，这个的 zero 这是什么？是 identity。然后我是用什么呢 ？transition matrix， 这个 P of T 是 differentiable，BC1 是 differentiable with respect to T 现在是 zero infinity。然后我们定义。Q 啊，没注意，这是一个 matrix。定义这样，另一个来定义好，这个叫 set to be the generator matrix。The process of NCTS. If that defines what QIJ defines I zero twice plus is the limit PIJ equals to 0 positive sign。这是 rate of the change for the transition， 这是不是 derivative 的定义，在零点的定义嘛？这是 PIJ 它的 derivative 在零点的定义，对吧？这是不是 derivative 在零点的定义？帮我看一下，对，如果 I 和 J are the same， 这个 what happened 是1，对不对？这一项是1 ，I and J are the same， 这一项是1，所以它是 the rate of the change， 这叫 transition rate。然后 I 不等于 J 的时候呢 ，I 不等于 J 的时候，这个 PIJ 0是什么？是0，所以它就是它。都是从 right hand side approaching 0。现在我现在还想强调的是，这是 column sum of the transition matrix 是等于1的意思。这个不需要是非得是 finite，infinite 也对，只要 non-explosive 就可以。那发生什么了呢？看一下 那 column sum Q 是什么？看一下，我们知道 Q 和 P 是怎么 related。Q 的 definition 是什么？是 P zero plus derivative， 对不对 ？Rate of change 在 zero， 这是它 definition， 这是 component wise definition， 这是 matrix， 对吧？这是 matrix definition。那这个是什么？这个其实就是什么 ？DDT zero transpose。然后这个后面，因为这个是 constant， 所以就是零，对不对？这样有没有清楚？它是在零点的这个导数，我们现在把它拿进去是 zero plus， 在这一点拿进去是它。所以说，换句话说，我们的重点是什么？重点是这个。如果你的 transition matrix， 我们要留住这个 transition matrix column sum 是 one， 那这个 generator matrix column sum 都是 zero。这是 zero matrix， sorry， 这是一个 zero column vector。Sorry， 这告诉我们什么？对角线一定是什么？是 off diagonal 的 sum 的 negative 要等于对角线，因为加起来要是零，所以这个是我们要 check 的方法。可是这个的好处是什么？这是一个 constant matrix rate。我现在就不推导了。Use Chapman-Kolmogorov equation。我们可以推出什么呢？可以推出这个 dpt 它是 qpt， 你不要混哦。这个 pt 是 transition matrix， 这是 generator， 这是 forward cohomology differential equation， 然后 p 在 zero 是 identity， 然后还有一个是 backward， 都是用的刚才我们说的 champion cohomology differential equation。区间你是 time 往前走还是往后走？还有一个是 p， 对。这好处是什么？我只需要知道 Q 了，我就可以 evolve。你看这个说明什么？这个大家会解吧？这是 constant， 这是 constant matrix。现在大家会不会解它？这个会对吧？是什么？这谁都会解。这是什么 ？Very good， 乘以 identity 嘛，对吧？就它嘛。这个怎么定义的？这就这么定义的，对吧？它是 matrix， 对吧？就这样定义的哈。所以我们就知道 Q， 这叫 generator matrix， 我就可以知道所有的 PUT， 就清楚了。像刚才 Laplace 的 case，sorry， 华松的 case， 它对应的 generator，sorry， generator matrix，generator matrix 是它的 generator 是啥？大家来看一下，华松的 case， 华松那个擦了哈，从这儿能看见，从这儿能看出来吗？这是它的 DI。1I 这个是从，假如说这是0，这是1，这是2，它这个是它的 birth rate，拿到新的 text message 的 birth rate，把 delta t divide 掉，刚才 probability 是 lambda 的 velocity， 那要算 rate 除 time derivative 就是 lambda 对吧？那这一项是什么？我们知道 column sum 一定是什么？这是没有 death， 因为是 zero message， 没有 death 对吧？也没有 death， 只有 birth， 只能是说 receive one new message or not。那这一定是什么？因为 column sum 是0，这一定是，对吧？然后这个一样啊，这是有一个 message， 那它下一个就变成有2个 message， 那这一定是负狼的，就这样写下去。这个是什么？我们看最后这样写还不太好。最后这样写，我没有 and， 因为它这是 infinity， 它的 size 是 countable many by countable many， 这个清楚吗？这是它对应的当中的 matrix， 这个就是它的 rate 嘛。刚才的 probability 是 lambda delta t 对吧 ？divided by delta t， let delta t go to 0， 是不是 lambda？ 那不就是它的 rate， 它的 derivative。刚才说了 Poisson process 的 birth rate 是 lambda delta t。它的 rate 是不是就是 lambda 当 delta？ 对，它的那个对应的 rate， 那它 column sum 如果是0的话，这一定是负 lambda 的，就这样子。那你看，知道这个，其实就刚才可以把它写出来，它就是这个 dPTPTQ， 你就知道东西怎么引爆了。所以现在就出来 second way to characterize a CTMC，which is way much better。是什么 ？Generator matrix 或 generation matrix 2个名字都会有见到过，就是这个 Q。Q 是什么 ？Transition rate。所以，当你要用 CTMC model 的时候，你要直接写出来会非常复杂。你只需要给一个 transition rate table， 这个 process 就 uniquely well defined。啊。说是个定理。这个就用 Chang-Hong homography differential equation 刚才那个定理，把它分开 matrix 写出来，推导出来就是这个。结果是什么呢 ？The transition probability。PPC satisfied forward satisfied forward differential equation。这样 forward 可以或者是 backward。这个，这是 forward， 一定会写 forward。你知道有很多 statistic， 比如说你感兴趣的 probability certainly happen， 或者是说你感兴趣的，比如说 mean first passage time etc， 他们很多都是用什么？用 backward homography differential equation， 用 one step method 你就可以推出。不是这个 differential equation， 是这个方法，它也是 backward homography differential equation。那这个 forward 是 capture 什么呢？是 how the transition probability evolve over time forward。How the probability evolve over time. Probabilities evolve over time given the current state. Backward 是什么呢？是说我 keep the final state fixed. Determination state fixed. 我想知道 how things evolve over time become this final state. Growth. 我想知道 how will the probability evolve backward in time. Probabilities evolve backward in time. 如果我们知道这个 Q 了，事实上就可以 uniquely 刻画这个 CTMC。比如说像刚才这个，你有了这个，用这个，比如说用这个，或者用这个，就可以讲刚才我们推那一大堆，这个 PIT 等于什么 E 的 lambda t，lambda t 的 i 次方除以 i 的 factor， 一下就可以推出来了。这个我们都知道怎么做，对吧？如果是 diagonal 是不是最简单？如果是 diagonalizable 这个最简单，怎么办？如果 Q 是 diagonalizable 的 ，generated matrix 是 diagonalizable， 会怎么样？diagonalizable。那你就会找到一个 matrix H 是个什么？这个 lambda 是什么？那这个时候就简单了，是不是？那这个 EQT 或者说这个 transition matrix over T structure 非常清楚是什么？我们知道是它，对吧？那它是什么呢？刚才我们定义了是它。所以它是什么？这个 lambda 是这个 lambda。就是对吧？为什么可以拿出来？因为这个 matrix multiplication 每个都可以拿出来，对吧 ？H inverse H cancel 嘛，只剩最头的一个 H 和最尾的一个 H inverse， 对吧？这很清楚。还有一种是说是解 ODE 的方法，大家知道解 fundamental matrix， 通过解 fundamental matrix 来解 EQT， 就是 fundamental matrix。Nth order differential equation。解那个 system 变成 first order， 它是一个 linear system 去解它的 fundamental matrix， 那就 EQT。而事实上，很多做方程的，不管你是 ODE、PDE， 我们都有这个叫什么 evolution operator 或者是 fundamental solution， 对不对？就是这东西。好，刚才之前我们讲过 discrete time Markov chain， 现在有个 embedded something called embedded Markov chain， 什么意思呢？在每一个 jumping point，Markov process 都 jump to 一个 state， 对吧？如果你 keep track only that state， 就是你 waiting for exponential time， 你 jump to another state，waiting for exponential time， you jump to another state。如果你 only keep track 那个 state， you jump， 得到对应的 process 就是 embedded Markov chain。对。这是 waiting time。X jumping。 为什么要做这个呢？我们把一个 continuous Markov chain 给它分解了，一个只关心它的 jumping state recorded by embedded Markov chain，还有一个就是 jumping time，把它分解了，或者是 waiting time。什么呢？就是现在这个 t replaced by random variable wn 是 n 次 jumping time， you evaluate the process n 次 jumping time 得到对应的这个 process， 每个 n 第一次 jump 会有一个，第二次 n 会有一个，你 keep record keep record all the jumping state， 这个 set。这个 set is called the embedded Markov chain。为什么要做这个呢？我们把 EMC 好了 ，embedded 第一次写全名嘛。有时候你读文章的时候还会看到一个叫，也可能会叫 jump chain， 一般都叫 embedded Markov chain。有的时候你可能还会看到一个名字叫 jump chain associated with CTMC。为什么我要做这个呢？我看一下这个 embedded Markov chain， 它没有时间的观念，它是个什么？它是一个 DTMC。那我们 DTMC 我之前做了，我做了什么 classification？ 所以只要你不涉及到任何跟时间相关的概念 ，nothing related to time， 你都可以用 DTMC embedded Markov chain， 它是一个 DTMC。我们知道怎么 classify DTMC， 你做了是吧？什么 irreducible、reducible， 什么 transient、recurrent 之类的，那个 classification 都可以用来去 classify 谁 CTMC， 只要你不跟时间相关。时间是另外一个概念，它不是一个 integer value anymore， 它是个 random variable。第二个是说，这个 concept is helpful on classifying the state of the associate CTMC。比如说，我们之前讨论那么多 ，DTMC 只需要一个什么？如果是好猫只需要一个 transition matrix。我现在换一个 notation，因为用了太多的 t 了。本来想用 t 又变成 time 了，所以我们用 t hat。可以不叫，只是个名字。 Sounds familiar？ 就是说，我们这么归结是说，把一个 CTMC 分解成2块。第一个 embedded Markov chain only record the jumping state, nothing related to time。第一次、第二次、第三次。但是还有一个 important information is missing. What that is? The jumping time or waiting time. We'll do that separately. 可是它的好处是说，我们可以用它作为一个工具去 classify 它对应的 CTMC。因为我们之前的所有 notation 都可以用来去做这件事情。那很显然，这个transition matrix 先看一个例子也是可以的，比如说。它对应的 embedded Markov chain， 我想知道它的 transition matrix 这样。这个是我们看到那个 Kaohsiung process 是最简单 burst and death process。Only has a burst， 你只有 retrieve 新的 text message， 你不会消失一个 text message， 除非你delete 哈。对，那是不是你没收到？是你收到你没有要。对，它的 transition 是说从0只能变成1，从1变成2，从2变成3，这个地方都是0。非常简单，是它对应的 transition matrix。你只有这样，你只有 give birth to 1 with probability 1，你没有别的。那 in general 呢是什么样呢？如果 state I is not absorbing，absorbing 是什么意思呢 ？absorbing 是 QII 等于 TII 等于1，如果不是 absorbing 是 QI 小于1，它不是 absorbing state。那这时候我对应的 embedded Markov chain， 我要从 state I 再转到 state I。如果不是 absorbing， 它就会是什么？它会是一个 transient state， 就你会 keep moving， 你 pass I 了，你会 keep moving， 对不对？那会怎么样呢 ？absorbing 是说 eventually 你会 come back， 对吧？如果你不是 absorbing， 它是一个 transient， 它会一直 keep going。所以这个 TII 就是它 embedded Markov chain 对应的 transition probability 一定是什么？一定是 0。因为这个 process must change at state I， 你不能 stay， 你不能 stay， 你只能 change。那如果 in general 呢，我们可以写出来这个 transition matrix 长得什么样，用 one step method 就可以了。是等于。是1，然后是从接到 I， 这用 definition，Q 的 definition 一步就出来了，这个是 Q U I Q I。Remember the diagonal 是 negative QII，QI 是负的，所以 negative QI 是正的。这个是说 Q I。这个是 Q I W， 这是 transit state， 这是 transit state， 这是 come back to the same state。如果一个 state 是 absorbing 的话，它这个 transition probability 概率会是1 ，otherwise 它就是0。然后 in general 这个用 definition QIG 刚才引入的 definition 那个 transition rate 写出来就是对，所以我们可以看到 CTMC 它对应的 embedded Markov chain 的 transition matrix 这是 constant matrix， 是用 Q uniquely 决定的，是长得这样子。 如果 no absorbing state without absorbing state。without absorbing state 没有任何一个 absorbing state， 就长得是这样的。Q0 Q2 Q4 是如果有 absorbing state， 如果某一个 QI 是零 absorbing state。What we're going to do? Then TII hat, as we define here, has E, and the rest of the column, the rest entry in the column are all zeros. The S column, all zeros. All zeros. 就是说白了，我的 CTMC 可以用它的 embedded macrogen， 这个只能 capture part of information， 只能 record 所有 visiting state， 然后用它来做 classification。然后现在我们想学的就是 CTMC 的第二个 characterization， 我不需要 remember 它的 P， 我只需要 remember the generator matrix， 我就可以 generate everything。刚才我们已经看到了，就是那个 EQT， 对吧？就是 Q，PT 就是 EQT。我们来看一个例子吧。来看一个例子。我们有一个 finite CTMC， 然后它的 generator。还是 the generator matrix Q 长什么样呢？想那个 Poisson， 这事实上就是一个 Poisson process with first rate lambda equal to 1。那这个 case， 我们想问的是 ，What's the corresponding embedded macrogen？ 然后这个 embedded macrogen 是不是 periodic 还是 aperiodic？aperiodic。然后，如果是 embedded macrogen 是 periodic 的话，那它对应的 7TMC 是不是 periodic？ 这个 EMC 我们去 capture 就只用什么？用 transition matrix 就可以了。它对应的 transition matrix。这 definition 所有的 QI 都在这儿呢，我们带进去就好了。应该就是0。如果有这 transition matrix， 能不能把这个图画出来？能。这是什么意思？我如果有4个 state， 1、2、3、4，这是从1到几？从1到2吗？这是从2到几？2到3。这从3到几？3到4。然后从4有什么？对，所以这是一个什么？这是一个 periodic， 它是 period 等于4的，是一个 periodic embedded market。那我现在问题来了，我知道 embedded market chain 是 periodic， 是周期是4的，那我对应的 CTMC 是 periodic 吗？大家听懂我的意思吗？如果我有一个 third cycle， 就相当于 clock 是 period， 实际上是24，因为我们开白天黑天，我说现在是12，对吧？那个 period 是12，是 embedded market chain。那它是 periodic， 是 12， 是那个周期是12的，这周期是4的。你能说它对应的 CTMC 也是 periodic 吗？刚才说了，我把 CTMC 分解成2个什么 ？embedded market chain， 这是 DTMC， 加上什么？还有个东西我没有 capture， 叫什么 waiting time， 那完全没有含在里面。我只是 capture 第几次 jump 在哪里，我并 jump 的 location， 我只 capture 它 state space， 我并没有 capture 它的 waiting time。所以我现在的问题是说，我如果知道 embedded market chain， 比如说它是 periodic， 或者有一定的 periodicity， 我能说它对应的 CTMC 也是 periodic。Why or why not？ 什么叫 periodic？ 直观上想，就是我可以在一个固定的时间，我固定的 time step， 我可以 repeat 一个 pattern， 对吧？那现在假如是周期是4，是说什么？第一个 jump， 第二个 jump， 第三个 jump， 第4个 jump， 我要回到同一个 state， 是这意思吧？但是这个 jumping time 是怎么了？我刚才讲了，这个是 CTMC 的 key point。jumping time 是什么 ？waiting time 是什么 ？exponential distributed 是个 random variable。所以呢，所以 CTMC 没有 periodicity， 它是 random 的。我说的意思，你这有4次 jump 嘛，对吧 ？T1、T2、T3、T4， 对吧？你从1又回到1了，是 state 你是回来了，但是经过的时间是不一样的，因为每次都是 random 的。所以 answer to the last question is no. Because what? Because 这个 waiting time random variable。都不用说它 exponential， 它是一个 random variable，random variable 它都是不定的，对吧？这样 make sense 吗？就像你想感染吗？可能这个时间，这个有一个，比如说下一个时间有一个人感染，再过几个小时，比如说5分钟之内有一个人感染，然后结果又过了1个小时有第2个人感染，然后又过了，然后几天以后才有第3个人感染，他每次的时间都是 random 的，你不知道多长。所以，即便 embedded market chain 它有 periodicity， 我想强调，你不能用它来定义任何跟时间相关的概念，因为这个 periodicity 是在 CDMC 要 capture 它所有的时间，是经过同样的时间你能 come back， 所以 answer is no。好，所以我们可以用 embedded market chain 去 classify， 你可以说什么时候一个 state 是 accessible， 什么 communication。什么 reducible、irreducible 这些我们全都可以做。我们讲一个，然后我们讲一个东西。好，然后我们来做点思维是吧？就我们今天讲的第一个结果，这个 embedded market chain 我们不是叫 YN 吗？我们假设它是 positive recurrent irreducible， positive recurrent。with condition matrix。行，这是从 从 J 转换成 I， 经过 n step transition，J goes to infinity。Sorry，n goes to infinity。从 J 走到 n， 用 n step。这个 limit 我们刚才早上已经见到了，这是什么？是 one over the average return time。如果是 aperiodic，period 是1，否则的话。这个 notation 真是不是很好，这是我们早上见的，这是 for DTS， 那 for CTMC 呢 ？All we need 这个 CTMC 是 irreducible， and positive recurrent。Again， 这个 irreducible positive recurrent 都用谁定义？用 embedded Markov chain。Then what happens? Then the limit 从 J 走到 I， 那没有 n 了，是 t。As t goes to infinity， 那是 continuous change over time。这个是什么呢？这跟这是有区别的，这是 QII。这是 diagonal entry，negative diagonal entry of the generator matrix 再乘以 mu i。Again， 这个 mu i 是它的 mean return time。这里应该再加一个，这个是 irreducible or periodic when di 是1。我想说的是说 CTMC 和 DTMC 它都有 long time behavior， 但是这个东西跟刚才这个东西是有本质区别的。第一，这个 CTMC 你不能 talk about periodicity， 我刚才用那个 example 已经看到了，即便是4次 jump 你就回来了，每次 jump 都是 random time total time 是 irregular 的。第二个，这个 long time asymptotic behavior 当时间 go to infinity 的时候，它是有 limit。这个 limit 和这个还是有区别的，区别在哪儿？是这个是负的 QIF。我们再讲一个 station probability distribution， 然后我们做 simulation， 好吗？我们讲一个最简单的定义好了，就讲一个，可以用 P 来定义，也可以用 Q 来定义。刚才说了两种方法都可以 uniquely determine CTMC。这全是 homogeneous non-explosive 的 ，OK？With generator matrix Q。然后这个 vector time of the process。如果这是什么呢？这个派是 Q 的 null vector，null vector 是什么？是 eigenvector associated eigenvalue 0。这个定义是最好做的，但是现在看起来不好理解。我再给你们第二个定义，两个是 equivalent， 我叫 definition one。我现在还是有个 CTMC。CTMC， 它是 transition matrix matrices P of T， 这是一个反例。然后，那这个派，它是 station distribution。如果 PT apply on 派 equal to 什么？我们见过了。我们之前做的只是 for DTMC， 是 P apply on 派 equal to 什么？它是它的一个 fixed point。我是不是见过了？现在难点是什么？要 for all T。而且还要满足什么？这个 column sum 是1，所有的元素是单个，只是 normalization。我说它的难度是什么？你要满足 ，sorry， 你要满足 not 1T、2T all the possible T。而这个 definition， 这个 Q 是什么？是一个 constant matrix。两个 definition 是 definition 1 and 2 are equivalent。什么时候？当 distribution distribution 是存在唯一的。什么时候存在唯一？我们已经知道了，对吧？ irreducible positive recurrent， 对吧 ？probability distribution 它是存在唯一的。exist。这个定义是不是很好理解？它是 stationary， 不管哪个 t 它都满足。那为什么这个对？怎么看？比如说这个对，为什么这个对 ？Suppose 我们知道 definition two， 我想推 definition one， 这个怎么办？怎么看？我想说的是这个好理解，这个看不出来，这个怎么看 ？Definition two 是 true 的话是 PT for any t 派等于派。然后 what we can do？ 如果我们两边求导数的话，我们得到什么？这是 constant vector， 它导数是什么？对，是0。然后呢？然后这个根据 homology differential equation dpt dt 是等于什么？是等于 qpt dpt dt 是不是等于 qpt？ 这是 homology forward differential equation， 对吧？我们刚看到了，对吧？哎，那这个是 qpt， 我们知道这个等于什么？等于什么？等于派嘛？根据 definition one， 是不是？因为它是 stationary 的。那这个是什么？这个就是 q 派，对不对？我说这个是等于派，它就 q 派，它就等于0嘛。反过来你也是可以推的，用 p 是等于 exponential qt， 马上就可以看到了，它所有的 power 都 vanish。好处是什么？好处太多了。你去解一个所有的 pt 等 pt 派等于派的 fixed point 和去解它的这个 null vector normalized null vector， 这个是 way more less expensive， 对不对？这是求它的 station distribution， 有没有清楚？这是 transition rate function， 这是 generator function，generator matrix， 这个是 transition probability matrix，they're different。好，那我们今天来看一个 example 吧。这个 SIR model， 我们直接做一个 SIR model 好了。大家了解基本的这个想法了吗？好，做这个，我来做一个 SIR model。我直接。 我们知道 ICR 里有3个 state， 这是 transmission， 这是 recovery。我们想 capture 什么？我们最关心的，假如说还是 close population， 我们最关心的是什么？我们最关心的肯定还是 I， 对不对？想看 I 怎么变。我看我刚刚code有没有发给你们。code有没有发给你们？有发给你们是不是？有。看一下啊，看我发的对不对？啊。如果我们 focus on I 这个focus on 这个 model 的话，即便是 close population， 我们需要知道2个 piece of information 才能 uniquely identify the whole process。我说的意思 ，we know S, we know I, we can identify R 是 N minus S minus I。说其中一个 component 我们 take 的一定是 I 嘛，另外一个就你的 choice， 你可以 take S，take R， 对吧？没问题，是不是？然后呢，现在在 keep track 的时候，事实上只有2个 event 可以。第一个是什么？第一个 possible event 是什么？第一个 possible event 是什么？的 event， 这个是 change， 这是 transition rate，infinitesimal transition rate。我刚刚说了，知道 generative process， 知道这个 process。我们第一个是 infection happen。如果 infection happen， 什么会 change？S 会变成什么？小一个，对不对 ？Infection happen will lose one susceptible。I 会怎么样 ？I 会增加一个，对吧？我现在说，我说既然 population 是 closed 的，我不需要 keep track of R， 对吧？这跟我们 SL model 一样 ，R 是 decoupled from the system，R 是等于 N 减 S 减 I， 对吧？可以吗？所以这里没有看到 R， 不是 R 不在 ，R 在 ，R 永远都在 ，R 是等于 N 减 S 减 I。S 是什么？来写清楚。我这 notation 你不要混哈，这个不是 ODE 的，这个 ST 是 number of susceptible at time t。I of t 是什么？是 number of infected individual at time t。然后 ST， 我现在假设 total population size 是 conserved， 它是属于什么呢？是0、1、2，一直到 total population size， 这是 maximum possibility。Same thing 5.5， 对吧？没错吧？然后你要做这个东西 ，no matter how many events， 你都可以做。那现在这个 case 会有什么？会有 infection， 对吧 ？infection happen 无非，因为我刚刚说了，不用考虑它是 sufficient， 就看这2个。如果 infection happen，susceptible 会 lose one， 我失去一个 ，become infected，I 会加1，对吧？这是 transition， 它的 rate 是什么？取决于你这块怎么写。你们记得这个吗？这是什么 ？beta S， 我看我用的是 density dependent 还是 frequency dependent， 我已经不记得了。我用的是 frequency dependent， 用的是这个 force of infection 是 frequency， 不是 mass action， 随便，那是你的 choice。然后是 gamma I， 然后这个地方是什么？这个是 minus beta S， 对吧？没错，这是我们 OD， 大家都非常的熟悉 ，is that right？ 好，那我说 any single time 只有2件事可以发生，或者 infection 或者什么，另外一个 event 叫什么 recovery， 对不对？好，如果 recovery happen 会怎么样？因为我不 keep track of R， 我说 R is out of picture， 我不需要 keep track of R， 是吧？如果 recovery happen 谁会变？对吧 ？I 会 decrease by 1， 因为你 one individual recover at that unit time， 对不对？好，我们先来看对应的 rate。那这个的 recovery rate 是什么？是不是伽马乘以它当前的这个 number of infected？ 这是它的 recovery， 在这个 time point 的 recovery rate， 对吧？那它的这有问题吗？这个现在要这件事情发生，它的 infection rate 是什么？是 beta S over N 是 constant， 对不对？然后乘以什么？这样可以吗？不管你有多大的多 complicated process， 你要知道你有多少个 independent event。为什么我当定义 rate 以后，我就定义了它的叫什么 generator process， 我知道它的 transition rate，infinitesimal transition rate， 这是 infinitesimal transition rate。来讲清楚，这个有没有讲清楚？不清楚，我们就开始来看。那现在就是唯一的，我现在知道了，我需要做任何一个 CTMC， 我就做2件事。第一个，从现在 clock time 0， 我要知道 what's the jumping time， 对不对？What's the jumping time， 对不对？你不是有一个 waiting time until first event happen， 我得知道我要等多久。第二个，一旦我知道我要 jump 了，我要变了，我要知道。我不管我100个 event 也是一样的，我要知道我变成哪个。我现在只有一个什么，一个 infection， 一个 recovery， 有没有？对吧？我要知道我变成哪个。Are you guys with me？ 那我们来看啊，咱一步步来。我现在有2个问题，第一个我们要解决什么 waiting time 的问题，对吧？这是 waiting time。第二个我要解决，我一旦我知道我要 jump 了，我等到 waiting time， 我要 decide which event going to happen， 对不对？不管你有1000个、100个都是一样的，怎么去解决这个问题？那我现在就要算，这个是 one unit time one event happen， 这是 second unit time second event happen。你是有2个什么 exponentially distributed clock。这是它的 transition rate。With this rate， 你 infection happen； with that rate， recovery happen。你有2个 exponential clock， 就是两个表，这2个表都是 exponential distributed with different rate。这是第一个表的 rate， 这是第2表的 rate。我现在得知道是哪个表先响，哪个表先响就哪个 event 先 happen。那换句话说，我得算这个 event happen 的概率和这个 event happen 的概率。那这个是可以算出来的。这个 event happen 的概率，我现在我就写它是 P1 吧，这是 P2，P100你也是一样的。那它发生的概率就是 P1 除以 P1 加 P2， 这是可以 rigorous derive 的，用那个 distribution。然后直观上看的这个是 how likely overall happen， 这是 the probability the first one happen， 这是 probability second one happen。然后当它俩加在一起就是你 normalize， 对不对？对，然后第2个就是直观的看，不是 rigorous derivation。我的意思是说，你这有100个 event 都可以这样做，是 P1 除以所有的 summation， 100个 event 的 summation， 就是它的 proportion 嘛。第2 P2 除以这所有100个 event 的 summation，P3 除以这个。我现在只有2个，足够了。为什么呢？你看啊，我现在是不是有2个数？我现在是不是给定这个 current state S 给人 cutting through the I， 我是不是有2个数？这是 P1 P2 嘛？我就会有2个，我叫这个是 Q1， 这个是 Q2。谁能告诉我？我现在里面只有2个 event，Q1 加 Q2 一定是什么？一定是1，对不对？好，那我就要 simulate 这个 process。如果我取一个 uniform distributed random number on 0 1， 如果我取出那个 number 可以是什么？可以是 anywhere distributed anywhere。如果这个 number 小于 Q1， 就是 probability， 相当于是 flip a coin。the probability 这个 coin 它的 likelihood happen 小于 Q1， 那就是第1个 event happen，otherwise 第2个 event。我这样说清楚没有？这样有没有说清楚？用这个来解决是哪个 happen？ 我有多少个 event 我都可以这样去做，就是我相当于是说我 randomly generate any number 是 uniform distributed on 0 1。如果我取出，当然每次都是一个realization。如果这个 number 小于 P1， 那就是 第一个 event happen。如果下一个下一个那个 number 是在介于什么？如果我有3个好了，我现在我这只有2个，我说我有3个，这是 Q2，这是 Q3。如果你下一个 number 是小于 Q1 加 Q2 的话，对不对？但是大于不是 sorry， 我说你 random generate 一个 random number， 如果它大于0，当然大于0，小于等于 Q1 的话，是 event 1。如果这个 number 是大于 Q1， 等于不没关系，它是 continuous， 小于等于 Q2 的时候 event 2。如果你有3个的话，是大于 Q2， 小于 Q3， 然后你就这样继续做，来决定你每次只能有一个 jump happen， 我要决定是谁 happen， 哪个 transition happen， 这是怎么决定？第2个问题。那现在还有一个问题 ，What's the waiting time？Waiting time 刚才知道了是 exponential distributed， 对不对？我们刚才已经证了。with some rate lambda， 我叫 mu 好了 ，some rate nu， 这个 nu 是什么呢？这个 nu 是由这个 p 加 p2 决定，因为2个 exponential curve， 它俩是 independent， 这是你的 transition rate。如果你 generating exponential distributed random number 有这个 rate 的话，你就可以决定 time。到 time 的时间再决定是哪个 event happen， 100个你是这样做的，这样说清楚吗？这就是你模拟。What's the probability something happen less than Q1? Something happen between Q1 和 Q1 加 Q2 就是 with probability Q2 嘛，然后继续做所有的。如果只有3个的话，这3个加起来一定是1。So far so good. Are we ready to see simulation? 我放一下这个，可以了。诶，看看。那个 code 叫什么呢？我们先看就看这一个，今天就好了。另外一个今天还没讲，我还没有讲 causal-stationary distribution， 还不知道是什么，我们下次再讲。这个就说，如果你认为 CTMC 是一个 appropriate model 的方式，我们怎么去做 simulation？ 我现在是受你刚才写了，我就给你说了几个 sample part。你真正做 simulation 想得到一个 statistic 的时候，这就是我不喜欢 stochastic method 它的 numerical part。你要算 10,000 at least simulation 去算一个 statistic，very expensive。所以很多时候你就想，能不能 theoretical 至少 approximation wise， 我可以 estimate 它的 theoretical result， 这个就 way better， 就是 asymptotic result。你明白我的什么意思吗？我说任何一个 statistic 去算。是3个 simulation nothing， 因为 anything can happen。你要做很多 simulation 去 collect 一个 statistic，very expensive。能做，但是我觉得不是很漂亮。Anyway， 我们来看这个。现在前面那个就是 clear setup 嘛，大家都很熟是吧 ？MATLAB 都知道的。第一行就是我 clear 我的 working background， 然后 close out 是我 close all the figures。这不重要。现在我是说我 total population size 是 1,000， 非常小的一个。然后这是我的 beta gamma， 然后 initially 我有10个人 infected， 有没有看到 I0 是 10， 所以 total population size 是1000，那个应该其实你就直接写成，先定义 I0，S0 就等于什么？不是 R0 等于0吗？然后 S0 就等于 n 减去 I0 你可以这样定义，对吧？9/9 whatever， 这是你的 initial setup。然后既然我画了3个 sample pass， 我就随便选了3个不同的颜色，这都不是太重要的。我们来看每一个 pass， 会画一个就会画其他的了。这是从0开始，这是 initial S 的 state、I 的 state 和 R 的 state。其实这里的 R 我们是多余的，这个 R 是多余的，你不需要的，这个 R 是知道的。OK， 然后我来 keep track of。我可以来 keep track of 所有的 I， 因为 eventually 我想授给大家 I 随着时间是怎么变的，我要把它 stack 起来，给它 collect 起来。然后这是我的 maximal running time， 这个 method 叫 Gillespie algorithm。Some of you guys probably have heard about it。这个 method 非常好的是什么呢？即便我现在做的是 simulation， 这个 method 是 exact method。Exact method 就是说每一步我做的都是 exactly what I want， 即便我是做 simulation， 也是 exactly follow the distribution 做 what I want， 它不是一个 approximation， 不像你解释 解那个 stochastic differential equation try 一些方法的时候，它全是 numerical approximation， 那个 error 可 accumulate 可以会非常的大，这个不是的。然后我们来看哈，这个是 infection rate， 我们刚才看到了对吧？贝塔 Si 除以 n，recover rate 是 gamma i， 然后 total rate 因为就2个。如果你有100个，你就把那100个都 accumulate， 用个 stack， 用个 sum 就 summation 就可以了。我现在只是这样写，你们都可以看得懂，对不对？有2个。然后 total rate 是 0 的时候，这个是说什么 ？either s 是 0 或者 s 0的时候，不对，是 s 和比如说 i 是 0的时候，这个 total rate 就是0，你就要 break， 这个 process 要 stop， 这个要退出，就是这个意思。你达到你的 extinction state， 然后这一项是干什么的？这一项 right here， 这个 dt 就是我的那个 capital T waiting time， 因为有2件事嘛，做 CTMC， 我们知道它的 key 是 exponential waiting time， 所以我要知道每次我要 wait 多久，这个就是去 simulate 它多久。我现在用了一个theory， 我事实上用了一个 theory。你可以直接用 MATLAB 就 simulate exponentially distributed random number with any rate you want。现在 rate 是什么？就是 total rate。你就2件 event 的 total rate， 它是 independent， 这个 rate 加，因为 independency， 那它俩在一起的那个 total event 就是 summation total rate。我说你不一定非得像我这么做，你可以 generate 用 MATLAB 就有。是 exponential distributed random number， 它事实上就用了我这个 line， 这个不重要，这是 dt， 就是那 capital T， 那这是 current time 加上 dt， 这是 update time， 对吧？我说的这个是 current time， 这是你的 waiting time， 这是你的 jumping time， 对吧？好，那现在如果这个 rand 就是一个 pseudo random number， 不知道中文怎么翻译，就是一个模拟的虚拟的一个 random number， 它是 uniform distributed on 0, 1。当你画很多 data 的时候，你看它的那个 distribution， 它几乎是 flat， 它是 uniform 的。Anyway， 这是一个 random number， 我 generate。如果它小于什么，这个就是 P1 除以 P1 加 P2， 我们叫 Q1， 对吧？小于 Q1 的话 ，infection happen。如果现在就这2种可能，我没有，我事实上不需要 update 它。我事实上不需要 update 它。如果什么？如果另一件事情 happen， 因为我就2个 event， 否则的话你要写什么？你要写 random number less than Q1， 下一个是什么 ？random number between 什么 ？between Q1 and Q2， 下一个是 between Q2 and Q3 etc。我现在只有2个，所以我就 else 了。这个是 infection， 这是 recovery， 这样清楚吗？这是 infection， 这是 recovery， 这样清楚吗？有问题吗？我就2个以，我如果不小于它，就大于它吗？大于它就是落在了第2个区间，就这个意思。因为第2个区间是什么？是第一个区间是0到 Q1 嘛，第2个区间如果只有1个的话，是大于 Q1 小于1嘛。它 random number 自动小于1，所以我落在第2个区间叫 else。这样清楚吗？有100个event你也会写，你就把所有的 independent event 找出来，怎么排序是你的 choice。你没有 unique 排序，你把它排序完了，我只需要选择第一个我需要多长时间，我等多长时间下个 event happen， 第2个我知道是哪个 event happen 就好了，怎么选就这么选，我选出来了，对，然后我就把它 collect 起来，因为每一次，因为我继续 update 我的 i 的话，i 就不见了嘛 ，i 就 current i， 所以 i stack 我只是把我的 i 所有 recorded 画出来，这样大家可以看到，我现在就把它画出来了。对。然后我现在这个画的是什么？这个虚线，这个 dash curve 就是 deterministic ODE 那个解 ，deterministic 那个 ODI 的解。然后这3个，你看那个这种3个带 color 的 curve， 它们都是 CTMC 的 numerical simulation。就是需要知道2件事情：第一，我要等多长时间；第2个，谁 happen， 就清楚了。Any questions？ 我现在有一个 suggest
Path 1, path 2. There are different conditions. Path
1. Oh no, same. Same. That's numerical simulation. What's the problem about random? 这是个 random process, 对吧 ？Stochastic process. Any simulation.
It generates the different values.
There is a zero probability you're going to see exactly two identical paths. 因为每一个 step 都是 random 的。Because every step is random. 我现在授你的是3个 stochastic realization, or we call simulation, 叫 sample path of the CTMC model. For what? For I. 这个说 initially 我有什么 10 individual infected. 然后这是 deterministic. 你也可以想象，当我做很多，那个应该给出它的 average， 就是我说它那个 average， 所有的 stochastic sample path 的 average 应该 very close to 这个 dash black curve， 对，是它的 mean 嘛，它的 mean。然后这个是我的3个 numerical simulation， 你们去 run 的时候一定跟我长得不一样，我敢100%保证一定不一样，否则那个 MLab 一定有问题。对吧？然后我有一个 suggestion， 我们现在做的是非常简单的 SIS， 我没有 birth and death， 你们可不可以回去加一个 birth， 加个 birth， 我就写到这儿，加一个 birth， 我们有那个 model 对吧？啊，加个 birth and death， 保证 birth and death 相等就好了，因为 population 要 close 嘛，否则的话你可以做，要不我再弄更难一点。对，先 birth and death equal 吧，你们试试看，可以吗？你们知道我说什么意思？就是这个 SL model。我现在说，如果你是 student 感兴趣这个，你可以回去试试，加一个 simple birth and death。你可以从哪儿 start？ birth rate 等于 death rate， 保证那个 population size close， 就是 BN，birth rate 是 BN，death rate 是 DS、DI、DR， 让那个 D 等于 B， 它就 DN/DT 等于0嘛。所以你还保证了 conservation， 看你们回去做一下能不能做。然后第二个 exercise 是 birth rate， 比如说大于 death rate 或者小于都可以 ，your choice。我建议是大于。这个时候你不能只能做 SI 了，你要做 SIR。我说的意思是，如果 population 不 close， sorry， 如果这个 population 不 close。这个 infection 你要定义成这个 infection 还是这样的 ，recover 你就真的需要这个了，你就真的需要这个了。然后这里这个不对啊，我现在只有2个 event 是 infection 和 recovery。当你加上 simple birth and death， 你有4个 events， 你有 birth、death， 我说错了，不是4个呢。如果是 open 的话，那个 death 有几个 death？3个 death。听我说啥？ Sorry， 我写下来好了。说这个意思。我们加个，我说这是我 suggest 的 exercise， 你看回去试试看。这是 birth 对吧？ recovery， thank you， recovery， 这是 death。Sorry， 这是 death， 这是 death。RDT 是等于 gamma I 减去 DR。我的 suggestion 是，你们先从 B 等于 D 开始来做。这个时候你可以 neglect 它，因为 conservation， 因为 S 加 I 加 R 它是 conserved， 我只需要 keep track 2个就行。然后再是 B 大于 D 的，这个时候我刚刚没说清啊，有几个 event， 我们来自己来数。是不是有 infection？ 这是一个 ，recover 是一个，有 birth 是一个 ，death 是3个。这个 death 是3个，取决于你有没有 conservation。所以这个时候 totally 我们会有几个？我们会有6个 events。如果是 not close population， 你要 keep track 6个，你会有 P1、P2、P3、P4、P5、P6， 然后去算 corresponding Q，OK？ 然后做一样的。你们要不要试试看 ？Do you want to give a try? You guys are going to have 2-week break. It's probably going to be really fun. In just a couple minutes, you can figure it out. Idea is the same. We already set up the time. All you decide is which event. You have more events, right? If your population is not close, you need to keep track of 6 events. 这样清楚吗？ Is this clear? Give it a try, if you're interested, of course. Anyway, I think we're going to call it a day. Yeah, it's really bad. Today is such a long day. Everyone's stayed here for 6 hours in a row. Yeah, it's horrible, right? But the good news, we're going to have a 2-week subsequent break, right? 2-week break. So we're going to meet on January 7th. So which will be 2 weeks from today. I hope you guys have a really happy and enjoyable Christmas and the New Year. All right, so that's it for today. Thank you.